Hey, my name's Ethan.
I'm Parker. And I'm Wes, and we're going to teach you computational fluid dynamics in SOLIDWORKS to calculate the force over a cylinder.
My name is Ethan, and I will be facilitating this lesson. To start, like we said in the intro, we're going to be using CFD. Do you guys know what that stands for?
Yeah, it's the same thing that I said in the intro, computational fluid dynamics.
Alright, so first what we're going to do here is we are going to create the cylinder that we'll be testing. To do that, I'm just going to make a simple circle in SOLIDWORKS. I'll extrude that a little bit. And then what I'm going to do here is I'm going to create a sketch so I can find the center of it, create some center line going vertically. And what I'll do is I'm going to do 2 extrusions on this center line. That's for construction. And those will both be revolved, or have a extruded revolve around them. Now, once we have the cylinder all finished up, we can save that. And once we have that saved in there, we can make sure that flow simulation is turned on. If you don't have that flow simulation turned on, you can go to the SOLIDWORKS add-in tab and just add that in. We're going to make a basic project name, 1 meter per second. First, we'll keep SI units, and making sure those are correct, we will make sure that it's an external flow. Obviously, we're going to be dealing with air in this case. Double click, next. It is adiabatic, which is correct. Now, velocity in the z direction, we're going to set that to be 1 meter per second. And I'll show you a little bit later how we're going to clone these, and we're actually going to make them edited under that section just to change those velocities. Here we're going to insert the global the global goal, which is going to be calculating that force over the cylinder, because that's what we are learning about. And you can see here, now what I'm going to do is I'm going to create that clone. I will make sure to name that clone properly. Once the names are all sorted out here, I will show you to actually edit that and have the correct velocity across the body. We're going to want to right click on input data, go to initial and ambient conditions, and you'll see right there we can change that right back to 2 meters per second. And then you can do that again for 5 and 10.
As you can see here, we have the computational domain.
Why is that necessary?
Well, the computational domain is necessary, so computation time when SOLIDWORKS is doing the flow analysis is at a minimum.
Here we can see that we are adjusting the velocity of each of the flows in order to make sure that we have those 4 different measurements at 1, 2, 5, and 10 meters per second.
So under the Tools tab, you can see we have a flow simulation. We're going to highlight that, and this is going to be triggering that bash run. And what we're going to do is solve bash run. We're going to make sure we mesh and solve for all of those different runs, 1, 2, 5, and 10. Then we're going to ask it to run.
Next, while creating the runtime environment, before simulation occurs, you can see here that mesh is created.
So what exactly is the mesh?
If I understand the mesh correctly, it is the system that SOLIDWORKS creates a rough outline or model to calculate individual points throughout simulation.
Yeah, that's correct. Like Wes said, it's kind of like a fishing net. It'll create different patches or points that are necessary before pre-calculation.
We can look at how many iterations we've gone through, the current value, and as it converges down to the correct value, it'll let us know how many iterations that takes. Now that progress bar does take a little bit of time. For all 4 of these runs, took my computer about 30 minutes or so. I actually went and got dinner while it finished up. Now, what I'm showing you here is just a heat map kind of the pressure that goes across the body and just the iterations to the conversion value I also just showed on that graph. These will both change live while you're actually doing them, so if you do need something to do while you're waiting, it'd be great to kind of watch those change. Kind of neat. So what we can see here is I actually just loaded in the values for 1 meter per second, and I'm gonna go down to this goal plot. I'm gonna insert a goal to actually view that force, which this is kind of an interesting thing that we have to do, because we already asked the CFD in SolidWorks to calculate this value, but this is just the way that we'll end up extracting it. So now opening up Excel, I'll make a quick plot with these values. So I'll start off with 1 meters per second, and don't forget to label that, and I'll put in that force value in newtons. So what we're going to do is, you can see in the next couple of moments, I'm just going to go through and extract all these different values from those goal plots just by unloading and loading in these simulation results from 1, 2, 5, and 10 meters per second. It'll be pretty easy and straightforward, and then what I'll show you in the end is a flow trajectory from one of them. We'll probably end up doing 10 meters per second because that has a really, really great flow. It's easy to visualize, so we'll add that right in there. All right.
So right here we can see that we're getting the values from the simulation and saving them into Excel so that we can have them later on to plot, and we'll talk about that with the students.
Alright, so I'm just wrapping this up by saving that Excel value so we can later make a plot in that. We'll talk about that with the students as well. But now what we're going to do is we're going to look at that flow trajectory like I was saying before. Selecting 10 meters per second, you can see I just right clicked and I'm going to insert a flow trajectory. Now, it's going to ask us to specify the surfaces. You need to do every surface on the object that you're looking at. If we say we're looking at a car, we would maybe only do the front hood, but in this situation, because it's going to be in the wind tunnel, we want to know all around it. Now I'm just confirming here that those pipes and the length of those pipes for the simulation results or flow trajectory results are what I want to be correct. And this is kind of what it looks like. You can see near the front we have some lesser values, and near the back we get greater values in red. And that makes total sense. As flow approaches, it's going to have a higher value, and you can see that again in the red. I think I'm going to specify this again in just a moment. But as that flow comes towards the cylinder, you're going to have a greater amount of force. And then we can see it will slowly disperse about the cylinder and cause some deformation of those flow lines.
When we visualize the flow around this cylinder, do you think that flow is laminar or turbulent?
Laminar.
Turbulent.
All right, we'll take a look at the Reynolds number because it'll actually prove it to us.
Here, looking at the Reynolds number, we can see that because it is greater than 4,000, it would be a turbulent flow.
Now, Parker, what type of line do you think that is?
Fresh Daniels, I would have to say it looks like a parabola.
Yeah, that's correct. It definitely looks like a parabola, which is super important, and it's great that it came out to look exactly like that. That is pretty indicative that
It is a correct model or a relatively close model of drag force as a functional velocity over a cylinder.